Big thanks to our sponsors, so Simulate Corporation, Taylor & Francis, Decision Lab, and CormSys from the University of Southampton. We really appreciate the support you've given us to help make this event what it is. And one of those sponsors, Selin from CormSys, would like to come on to say, just give a few words about CormSys.
It's like 15 years back. Good morning. Welcome, everyone. And thank you very much, Sean, Sally, Christine, Luke, and everyone else for an excellent program that we are all looking forward to. I wanted to say a few words about CormSys, which stands for Center for Operations Research, Management Science and Information Systems. First of all, because all the names from Southampton that you know are members of CormSys, and we are extremely proud of who we are, and we would like to spread the word so that it can open new collaborations, hopefully beyond our own local community as well. So we are a center that is comprised of several members within University of Southampton, but in particular, it is a composition of two groups. One is the OR group in mathematical sciences, where Christine and I proudly belong to, and the other one is Southampton Business School, in which the Department of Decision and Analytics and Risk, almost everybody in that group also belongs to CormSys. In addition to that, we have some members from other schools, such as life sciences, and several people in engineering also engage with us. So we are a large group, and at some point we were the largest of our type within the UK, and we have a very rich history. We were just talking with Sally. CormSys has been around for 25 plus years, and nowadays we see similar research centers exist in several other places as well. We are continuously growing. At the moment, we have 40 plus faculty members within these two schools, and we have 70 PhD students. And I must say that I'm very proud. Some of them are here, and actually we have an undergrad here as well today joining us for this conference. And this is the first conference workshop that students are joining. Some of our first years are joining for the first time. So it's very exciting. So in terms of research, because of this intersection of the different groups in different schools, we are very broad, and several disciplines are quite core to us. One of them is optimization. We have broad expertise, especially in the OR group, and operations management, revenue management, and of course, simulation. There are several people within CormSys who will contribute to simulation. So it is one of our major research areas. And we are quite proud, as I said, with our research output. This year we have been ranked as the 39th in the world in OR and statistics, and we are 7th in the UK. I'm not a big fan of ratings, but this is like, you know, something that at least shows that we are quite serious in our research. And as I said, we are one of the largest groups. So what we are really proud at this moment is also our relationship with the industry. And one of the key drivers of this is that we have a business advisory board, and Sean is a member of that. We keep this contact with 150 people from industry, and they advise us in how to govern our taught programs as well. And that would bring me to the fact that we manage as CormSys the external dissertation of 6 MSc programs. And these are listed here, which hopefully also shows our breadth. And with these MSc projects, PhD collaborations, and KTBs and further research, we are able to deploy some tools for several partners in industry, in government, NGOs, and beyond. And that's just a snapshot of who we are. We have been quite successful in our relationship with our society as well. And the MSc projects that we govern with these organizations have been quite impactful, which we can see in the last few years Higgs Awards. So just a little bit of like advertisement, if you take it, for CormSys. But the message that we would like you to get from here is that we are quite passionate about who we are, the OR research, the MS research, and nowadays actually data science research that's going on within CormSys. So please engage with us, keep the conversation going. We have regular seminar series that we would like you to attend, give seminars in, and send your PhDs along. And that's it. So thank you very much. I will now invite Christine to introduce the keynote speaker, I believe. Enjoy the conference.
I will wait if everyone leaves in and finds their seats and get you there. Welcome again from me from Southampton. It's lovely to have everybody in your home city. It has its downsides and its upsides. I'm not going to say a lot about Raghu because I want to hear from him rather than you listening to me about all the many things he's done. So Raghu has a PhD from Purdue in the US in 2005. So I think we've just worked out we did graduate from our PhDs at about the same time. And somehow it makes me feel very grown up now that I remember back in 2003, we were both PhD students in New Orleans and we were going to the bar. This is my rat story. I remember going to a bar in New Orleans with Raghu, and I think it's the first time I've seen a rat on the bar. That's my memory of that conference. And that was where we first met. So I think even at that point, you could tell that Raghu was destined for great things. And now I feel like we're both grown-ups. I'm introducing him as giving a keynote at a conference. So it feels like those 20 years have just flown by. So after his PhD in Purdue, Raghu went to Virginia Tech, but is now back in Purdue as a professor in statistics there. And that's his passion is the stochastic optimization, simulation optimization, and then kind of some of the statistical methods that go alongside the analysis of the simulation output, which is what he'll be talking about a little bit today. So he's a past president of the Informed Simulation Society, which is, I guess, the equivalent of our simulation special interest group in the OR Society, but probably a little bit, as a bit for everything in the US, a bit bigger than the SIG is here. And also very well known within the Winter Simulation Conference community, which is the big conference, usually in the US, that people will aspire to go to and get their papers in the simulation community worldwide. So I am going to hand over to Raghu because I can see his talk looks very interesting, and I was looking through his list of papers. This is recent work, so talking about cutting edge kind of simulation stuff. But I'm looking forward to it. Great, over to you, Raghu.
Thank you. Thank you, Christine. Okay, good morning to all of you. Thank you again, Christine, for such a kind introduction. It is such an honor to be here in beautiful Southampton, to be able to speak in your midst. Let me start by thanking my co-authors. These are four of my main co-authors: Peter Glynn at Stanford University, Dashi Singham at the Naval Postgraduate School Operations Research Division, Ziwei Su, who was my student in Purdue, who is currently now in Northwestern, and Yingche Ye from the National Central University in Taiwan. I also want to thank as much these giants on whose shoulders I stand, to invoke the words of Isaac Newton in his correspondence with Robert Hooke, I believe. Let me explain. So, over the last 30 to 40 years, what has happened in simulation is that we've realized that simulation is an exceptional tool at estimating objects associated with stochastic processes. We are really, really good at estimating these objects, complex systems, as we have seen, even yesterday, for example. But what we are not as good at, I think, is in addition to estimating objects of interest, we're not as good as at also reporting, for example, uncertainty measures. So that's going to be one of the first messages that I'm hopefully going to send to you, to urge you to, alongside producing estimates of interesting objects, to also provide uncertainty measures. And the second message that goes alongside the first is that this uncertainty measure right now, primarily due to the work of people of this sort, has become relatively easy to do through a method that I'm calling batching or overlapping batches. So hopefully as we go through the talk, this will become very clear. Now, for easy absorption, I've divided this talk into about 6 modules, A, B, C, D, E, and F. I hope I have I'm going to actually stop right after module B, module C, module D, for example, for about 30 seconds to a minute, just in the hope that I will get questions. Right? So I want to have the good fortune of not finishing my talk due to having many, many questions from the audience during those breaks, for example, so that I don't run away, because as the talk progresses, it's going to get more and more mathematical. So it'll be good to actually stop and discuss. Okay, so today's talk is all about what I call statistical inference for simulation estimators. So I'm going to talk about this within the specific context of simulation. Okay, so in order to do this, we need to first understand module A, which is what is statistical inference for simulation. Let's state this very simply. So let us suppose, for example, that you're looking to estimate the fraction of smokers in the population who develop lung cancer. Let's say this is your objective, right? So this is a very nice question to be able to answer. What would you do if you are faced with a question of this sort? You do something that's very reasonable. You'll go out in the population and collect a sample, right? So let us suppose that Y1 is the first smoker, Y2 is the second smoker, and so on until Yn is the nth smoker. You track each one of them, check, what fraction of these N smokers actually go on to develop lung cancer, and you'll report that as the estimate of what I'm calling theta. Theta, remember, is the fraction of smokers in the entire population who go on to develop lung cancer. We wish we knew that number. We don't know that number. And this is precisely why we are sampling in the first place. Okay? So this is fair enough and easy enough, and it's quite reasonable. The problem we have here is that if you repeated this experiment, if you went in out there and collected yet another data set of smokers, you're going to get a different value for the estimate of theta, right? The question of statistical inference in a nutshell is about quantifying how much that estimate is going to bounce around or fluctuate in service of estimating this object that we do not know. So loosely stated, that's what we are going after. And I hope you recognize that this is very important, and especially important for us who deal with simulation, particularly stochastic simulation. And often we are in the position where we are attempting to estimate some object we do not know. We go in, make our simulation runs, we get an estimator. If you repeated that experiment, you're going to get a different value. So it would be important for us to understand how we can quantify the amount of fluctuation in this estimate. Statisticians have thought about this for a long time. And over a period of time, the question of estimation or statistical inference has come down to about 5 objects that I will summarize now. So like I said first, theta, something that I would like you to carry as we go through the talk. I'm going to be consistent in calling theta as the object that we wish we knew. We don't know it. If we knew it, we wouldn't be doing these experiments. Theta hat n is the estimator that we get as a result of doing our experiment. N refers to the number of observations, the amount of effort that we make in running our simulation. It could be any of that, right? So theta hat n is what I'm going to call the estimator. Theta is what I call the parameter or the performance measure. Now, important, theta in the lung cancer experiment could be a real value, a number, a fraction, right? Theta hat n does not coincide with theta. It's probably going to be a little off. Theta can be a double. It can be a vector. It could, for example, be, the 90th percentile of waiting times in a toll booth and the amount of emissions, for example, expected emissions. So it can be a double, it can be a triple, it can be any vector. Likewise, we have an estimator for that. It could, in fact, be an entire function. Think of a situation where you're looking for the expected path of a hurricane, right? So the red curve here is theta. It's an entire function that you wish you knew. You don't know it, and so you run your simulation. I seem to have lost my pointer, now that's okay. So theta hat n is the estimator associated with theta. And in this case, it is an entire function. Now, in constructing or in going through this object or this uncertainty estimation, maybe I could move this thing over so that you're able to see this. Okay, so two of the key objects that are involved in estimating or quantifying uncertainty is what I call the variance and the bias. Variance or bias in a nutshell is the average error of the estimator theta hat n, where the averaging is happening across practitioners. Think of lots and lots of practitioners who are performing the same experiment. Each one reports a theta hat n. You're averaging it. Theta is the quantity that you wish you knew. It's the average error, quote unquote. Variance is the amount of fluctuation. Now, when I was a PhD student, my advisor used to display that this picture right here, which I thought used to be very, very useful. So on the top left corner, you see a bullseye there. The bullseye, the center of the bullseye corresponds to theta. That is the object that you wish you knew. And all of the blue crosses represent estimates that individual practitioners got. Because if you repeated this experiment, you're going to get different estimates. Now, the top right, top left corner, they're amazingly consistently incorrect, right? They're repeatedly coming up with roughly the same number, but they're all wrong. So we say the variance is very low there, but the bias is high. Now, the diametrically opposite situation is the one on the top right column, where the variance is very high, meaning that they're all over the place. The individual practitioners are all over the place. But on average, they appear to be right. Right? That's the diametrically opposite situation. The bottom right corner, everything's working perfectly. They're consistently correct, quote unquote, low bias, low variance. And the bottom left is high bias, high variance. They're wrong and they're not mixed. Right? So variance and bias are objects that you want to report with your simulation alongside theta hat n. Remember, as a practitioner or as a simulationist, you're reporting off late only theta hat n. Right? Repeatedly. It's only in rare cases that we are good at reporting uncertainty estimates alongside it. So the hope is that we will be thinking about reporting variance and bias as well, because these are very useful objects. The third useful object is what I call a confidence region. A confidence region is as follows. So I think it's useful to think of the top right corner. That picture right there, theta is a double, right? It's a vector. And there's one ellipse right there in the middle with the red dot. The red dot doesn't move, right? But different practitioners are reporting the blue dots. Each practitioner is going to report theta hat n. But alongside that particular theta hat n, I also want to report possibly an ellipse that looks like that, with the potential guarantee that the probability of the true object data living in that ellipse is 1 minus alpha, where 1 minus alpha some number that you wish. So for example, if alpha is 0.05, 1 minus alpha is 0.95. So with 0.95 probability, I want across practitioners that get there. 95% of the ellipses reported by practitioners will contain a true object. Any individual practitioner, it may or may not include it, but if you take this ensemble of practitioners, 95% of them will contain it. Okay, so this is what is often called the confidence region. I think it's a very useful object. This is one other object that we wish we will report alongside theta hat n. There are two other things. One is called hypothesis testing. You may have seen this in a basic statistics class. Hypothesis testing is a close cousin of confidence region construction, confidence regions. The last one, which is my favorite, is a prediction region. I will not talk about this because I don't believe we have time to do that. So we'll just focus on just constructing confidence regions because it encompasses a lot of, it encompasses theta hat n, it encompasses variance, of course, it is because it's a close cousin of hypothesis testing. Thinking about confidence regions construction is a good idea. So we'll focus the rest of the talk on thinking about how to construct confidence regions in general. And in particular, I'm going to outline what I hope you will walk away thinking, that's a really trivial method to actually construct a confidence region. Okay, so if we took the first example, recall the first, how I introduced this entire talk. I said, I want to compute the fraction of smokers who go on to develop lung cancer. It's a really simple example. What has happened over the last 30 to 40 years is that these scenarios have become more and more complicated. As data has increased, as computing has increased, the objects that we are trying to estimate has become more and more complicated. Even in yesterday's talks, through the sessions, the objects tended to be more and more complicated. And simulation in particular presents objects where inference or statistical inference has become increasingly complicated. Let me give you 3 examples. Without getting too ahead of myself, this notion of statistical inference is not new. It's been, statisticians have been thinking about this for 200 years. You see all the famous names right there. And like I noted, over a period from the 1700s all the way to the 1990s and now, for example, like I said, the thetas that we have been attempting to compute have become more and more complicated. Best illustrated through a couple of examples. So let's think about this slowly and carefully. So let us suppose, for example, that we are trying to compute, let's say, the 90th percentile, a confidence region on a quantile. Let's say I want to compute the 90th percentile waiting time in a toll booth. So you see a toll booth there. And what are the y's here in this case? Let's say y1, y2, y3, and so on, in analogy to the smoker example. Y1 is the waiting time associated with the first car coming out of the toll booth. Y2 is the second car, and so on until Yn is the nth car. Theta, the object that we wish we knew, let's say is the 90th percentile waiting time. And the question I'm trying to answer using simulation, for example, is I want to use Y1 through Yn to find, let's say, the 95% confidence region on this object that I'm calling theta, right? So if I were to only estimate theta, that question is easy. We're all experts at it. Right? So we're just going to evaluate all of these objects. We'll order them and take the 95th percentile of these and report it. But what we want in addition now is we want a confidence region on theta, a 1 minus alpha confidence region on theta. So quickly from the smoker example to this example, things have become far more complicated. Because no longer do we have a situation where we are just trying to estimate a fraction. We're actually trying to estimate an object that is much more complicated, which is the 90th percentile. So let's keep track of these 3 things that are going to show up all through the rest of the talk. Theta, this is the object that we wish we knew. In this case, in this example, it's the 90th percentile wait time. The data that we collect, Y1 through Yn. I'm simply calling it data. Theta hat n, the object that we are very good at computing, right? So we are very good at getting this. Hopefully we are going to find a way by which to, in addition, also report a confidence region. Second example, going backwards. Second example, very carefully chosen again to just give you an idea of the breadth of what we have been doing off late. This is a confidence region on the solution to a stochastic partial differential equation. This is often called the Euler-Bernoulli beam. So what you have here is a cantilever attached to a wall, right? And the cantilever, when it's subject to forces, it tends to bend, of course. And there is some amount of stochasticity in how much, the extent to which it bends. And there's also stochasticity in the forces that are involved, right? You don't know, you don't know where you're going to use this cantilever beam. So F here, that I'm representing as or denoting as a force, is going to be random. There's also stiffness associated with a particular beam. So depending upon the force that you exert and the stiffness, you can actually solve a partial differential equation to tell us precisely how much bending is happening. Okay. Now, this is not relevant to what I'm going to talk about today, but rest assured that this can be done, okay, with some effort. But the main problem that we are facing is that this deflection or this bending is itself random. It's random because, the beam that you're getting is going to have a random stiffness, and it's going to be subject to a random force. So the extent of bending itself is going to be random. And so in this case, for example, the theta that we have is the expected amount of deflection. Deflection itself is random. The z that I have here is a label that I'm giving to a random beam, quote unquote. The y1, y2, y3, and so on till yn, this corresponds to the first beam, second beam, third beam, and so on until the nth beam. Each one of these experiences some amount of deflection, and I'm looking to find a 1 minus alpha confidence region on theta. Okay, so hopefully the problem is starting to make sense to you. All of these are really different contexts. I have an object that I want to estimate that I'm calling theta. I have data that I'm somehow obtaining that I'm calling y1 to yn, and I'm looking for a confidence region on it. Here again, notice pattern, theta, y1 through yn, theta hat n, very good. We are very good at reporting this. We are looking for a confidence region that ensures this sort of a guarantee. I have a third example here, but hopefully I've made this point very clearly. This is an example associated with stochastic optimization. This is the classic machine learning example that you see these days. I'm looking to identify handwritten digits. And you have a very similar situation where we have a theta, which is the minimum of an optimization problem. Y1 through yn are data associated with the labels. And theta hat n is the estimator that we can get using this data that we are very good at estimating. And I'm looking for a confidence region such that probability of theta living in that region is equal to 1 minus alpha. Okay. Now, let me stop here for just 30 seconds to a minute to make sure that we have internalized the question so that we can, it doesn't get away from us as we go forward. So feel free to ask a question. Okay. So perfectly clear. Seems let's move on. Yeah, feel free to just slow me down, stop me as we go further down. Okay, so we have a situation again where, just to summarize this question again, object we wish we knew, data that we have obtained that we can use to compute an estimator that I'm calling theta hat n, which is an estimator of theta. And I'm looking to go further and construct a confidence region that ensures that the probability of theta living in that region is 1 minus alpha. Okay, now in in the late 1800s or really early 1900s, there's a really amazing statistician named William Seeley Gossett. He was a Britisher who was faced with this very problem. He was working in the Guinness Brewery in Dublin, and he was faced with a very similar problem where he was actually analyzing data on the quality of beer, for example. And he did something that really entirely changed the course of statistics. So let me explain what he actually did. In his situation, at least, theta was very similar to the lung cancer example. The theta was the expectation or the population, it is the average or the population mean associated with a random variable called y. And what he did is what we would do, which is go through and simply take a sample and compute the sample mean of it, just as we did in the lung cancer example. This is not a surprise at all. He also computed what we call a standard deviation these days, right? So take the individual objects that are called yj's. We have a theta hat n. Take the deviation of yj from theta hat n, which is the sample mean, square it, average it, take a square root. So sigma hat n here is a standard deviation giving you a sense of how much variability you're actually seeing in your theta hat n's. All of this is perfectly fine, things that we would have done. But Gossett's amazing discovery is the following. He demonstrated that when you actually take your theta hat n, which is your estimator, subtract it off from the true object that you know, divided by the standard deviation square and multiplied by square root of n, it has a distribution that is invariant, that doesn't depend on theta, that doesn't depend on sigma squared. Remarkable fact, right? So this came to be called the student's t distribution. And we actually have tables in the back of pretty much every statistics textbook right now, right? So this went on to change the history. And why is that? Why is this so very important? So very important because just on the basis of that very fact, just because this object that we just saw is independent of theta and sigma squared, we can actually show that this interval that we usually give, theta hat n minus some quantity that we now call a critical value associated with a student t distribution times sigma hat n, which is the standard deviation divided by square root of n. We are subtracting that object, adding that object to the quantity that we usually compute. And we report this as the 1 minus alpha confidence interval. And this comes simply from one or two lines of algebra. Okay, and all of this happens because of his discovery. Now, the obvious question is, so why can't we do what Gossett did, right? So we have the y's. We are very good at computing theta hat n. So why not just do what he did? We have theta hat n, compute a standard deviation, hope that if you actually perform the calculations such as theta hat n minus theta times the root n divided by sigma hat n goes to a student t, then we are all set. Just compute a confidence interval. The problem is that, the question that William Gossett considered was his theta was an expectation, just as in the lung cancer example. But in the three examples that I gave you, theta is far more complicated. In the first example, it is a quantile. In the second example, it is a solution to a partial differential equation. In the third example, it is a solution to an optimization problem. So what Gossett did is no longer valid, simply because you can actually see that simply by looking at this object. Think about what this object is. So in the lung cancer example, these are ones and zeros. Either the person developed lung cancer or not. This is the fraction of people who develop lung cancers. So these are apples and apples, right? Whereas in a situation where you're computing, let's say, a quantile, this is a quantile estimate computed across waiting times. These are waiting times. Waiting times and quantiles of waiting times They're not apples and apples. You cannot subtract them like that, right? Or you can take another example where this is the solution to a partial differential equation or the solution to an optimization problem. These are individual data. You cannot subtract them off like that. So it doesn't immediately transfer. What Gossett did does not transfer over immediately. But we can try to mimic Gossett using a very simple idea that I'm going to call batching. How do we exactly do this? So here again, maybe 30 seconds, a break for about 30 seconds to see if there is a question. Yes.
I think I have a question, but it relates more to the first
Please.
section. How do we know we've actually collected enough data to make a good estimation? So how many Ys do you need?
Yeah. So in a nutshell, the answer is we don't know. But the point is, how much ever we have collected, our uncertainty measure will reflect how much data we've already collected. If you have collected too little data, our uncertainty will be high. If you have collected lots and lots of data, our uncertainty will be very low. So the point is, given the data that you have, our uncertainty metric will reflect how much data you already have. Hopefully that makes sense. Yes.
Can you jump back into the slides? So one more. With this one, we've got Gossett's discovery. It seems like you have to know what the actual value, the true value of data is, but obviously that's what we're trying to estimate.
Yeah.
Like how do we form? Is it having Gossett go about forming that calculation since it's reliant on something that you know?
Yeah, excellent question. So I claim that this is an amazing discovery. The fact that this actually goes to a distribution or is equal, it has a distribution that's exactly equal to the student's t, independent of theta and sigma square. The question is, but we do not know theta. So what do we do with this object? Well, it turns out that because this goes to the student's t, which doesn't depend on theta or sigma square, if you look at this calculation with a little bit of algebra, the fact that this object's distribution is known, you can massage this over and write it in this form, right? So you can take this object, the probability of this object greater than or equal to something that we typically call a critical value associated with student t, massage or do some algebra on it, and then notice what you can do with it. Notice here that theta, this statement right here can be written in this form. These two forms are exactly the same. So the probability of theta living in between these two quantities, look at the left side and the right side. They have no unknown quantities. This is precisely why we call this a confidence interval. Yeah.
There's also an interesting aspect that if you use accreditation theory, that you can replace not simply theta, but by a known function. Looks just
Yes, yes, indeed, yes. Okay, fantastic. So where are we now? So the question is, hopefully I've convinced you that we cannot directly do what Gossett did, right? We need something more because the key part of the calculation was the calculation of the standard deviation. The yi and theta hat n are not apples and apples. We need to do something about it. So I claim that we can do what is called batching. What is batching? Well, before we go to batching, notice that there are three key objects in what Gossett came up with. The estimator, we all know how to do this really, really well, even in complicated situations. Sigma hat n, really key object. I've not told you what to do about that. And this object that is usually called the critical value associated with the student t distribution. So this is okay. I've not told you number 2 and number 3. So we need to focus on those. This is probably the most important slide of the entire talk, because the whole idea of batching can be encompassed using just this one picture. So recall that we have data y1 through yn. right? This can be complicated data. So what I do now is, instead of actually directly comparing yi with theta hat n, I take the data and I divide it into batches. The first batch consists of data y1, y2, and so on until y sub m. So I've taken the first m observations coming out of my simulation, perhaps. I create a batch out of it. The second batch overlaps with the first, starts with the d plus 1th observation, goes all the way up until d plus mth observation, and so on. The third batch goes from 2d plus 1 up until 2d plus m, right? So in this way, I've created a bunch of batches. Now, just as I computed theta hat n with the entire data set, I can compute individual theta hats from each one of these batches. Key point, right? So I take the first batch, do whatever I will do. So to give you an example, in the toll booth example, I can compute a quantile estimate from the first batch. I can compute a quantile estimate from the second batch, and so on, right? Let's see that using some notation. The first batch gives me a theta hat 1, comma m. The second batch gives me a theta hat 2, comma m, and so on until b batches giving me a theta hat b, comma m. Why is this important? Well, all of a sudden, I have something that looks like a standard deviation, because individually, I have b estimates corresponding to theta hat I, comma n, subtracted off of the grand estimator, which uses the entire data set. And these two are apples and apples now. I can think of deviations of this with respect to theta hat n. And I can do what Gossett did. Okay, so the idea is as simple as this. Instead of actually treating the individual observations, you batch them. And each batch gives me an estimate. You do what Gossett did after that. Okay, so now we have the complete algorithm. The complete algorithm is precisely what Gossett did. Theta hat n that uses the entire data set, sigma hat n OB. I'm calling this a different sigma hat n because this is obtained by taking the individual batch estimates, computing a standard deviation from it. Don't worry about this factor m over kappa 1. This is just a factor that is needed to make sure that it's unbiased and so on. So we won't worry about that. So this is precisely computed as Gossett did, but taking into account the fact that you're batching. And then we also have another quantity which corresponds to the critical value, right? So this interval should look awfully similar to what Gossett had. Gossett's confidence interval looks like this: theta hat n plus or minus student's t critical value, sigma hat n divided by root n. Our confidence interval, OB stands for overlapping batches. Don't worry about this S for the moment. This looks like theta hat n plus or minus some quantity. We do not know what this is. Remember how Gossett got this object. He actually showed that root n times theta hat n minus theta divided by square root of, or divided the standard deviation goes to a student t distribution, right? That's how he got these critical values. We don't know what it is in our case yet. These two are perfectly analogous after batching. So now the question simply comes down to, what is the analog of William Gossett's student t critical value in the batching case? So it came down to a very narrow question, which is analyzing or identifying the analog of the student t critical value in the batching situation. And this corresponds to the mathematical highlight. For many, many years, for about 2 decades or so, people in the simulation community were simply using William Gossett's student t critical value in here as well, right? Over the last 10 years or so, we've been able to identify the corresponding value by identifying the analog of the student t distribution in the batching context. And the name for that distribution is what we call the OBS distribution. And that's been identified, but more importantly, we have an analog of the student t table. we have OB, or overlapping batch critical values. So instead of William Gossett's critical values, in a complicated scenario where we are actually using overlapping batches, we have a corresponding table. I'm happy to provide this to you by email or even particular values. Okay, so we have corresponding a slightly different method. For example, in here, notice, for example, that we could instead of actually using a grand estimator of this sort, I could have averaged all of these. So we have a corresponding method for that as well. Not very important for the purposes of this talk. So I will skip that. Now, everything that I've discussed thus far was in the context where theta hat n, or the object that we are trying to compute, is a real value. Think about a quantile, right? The analogous situation I advertised right in the beginning, that this actually extends also to the situation where theta itself is an entire function, like this red line. Think about the trajectory of a hurricane, right? So this is the time-dependent path of a hurricane, for example. So does batching extend in that case as well? Yes, we do have the corresponding situation there as well. We have separate values for the student key tables or student key analog tables there. I actually went in and I did some numerical experiments to actually illustrate this fact. So let's think about the Euler-Bernoulli beam that I was talking about earlier. Think of the situation where you have different beams. Each beam has a random force acting on it and a random amount of stiffness. Recall that deflection itself becomes random. And let's say our theta in this case is the expected deflection, constructed as a function, right? At different x locations, the extent of the deflection is going to be different, right? So how would we do this with batching? Well, gather force and stiffness data, solve the NPDEs, the partial differential equations. Each one of these solutions is a deflection. It's a random deflection. I call these y sub j. I batch to obtain the grand estimator that I'm calling theta hat n, the individual objects that I call theta hat j comma m, construct the 1 minus all alpha confidence band using the critical values that I calculated. And here is an actual calculation using MATLAB, for example. So this is the 75% confidence band of the deflection of the beam. That is the 99% confidence band associated with the deflection. Okay, let's stop here again for 30 seconds. Yes.
You look at your chart that gives the student key critical values when estimating confidence intervals of simulation output. How far off are we using student key as opposed to the student overlap batching?
Yeah, excellent question. So the short answer to that question is that depends on the extent of the overlap. If you overlap these batches significantly, so in other words, let me go back to this picture right here. These batches, in a situation where these batches overlap significantly, and I would argue that you should overlap significantly. Why? Because if you choose these batches to not overlap, you're throwing away information that you have from your data set. If you overlap them significantly, the student T distribution and the OB distribution that I was talking about can be off by as much as 25%. So it's a significant difference, and the confidence intervals or confidence regions will be incorrect if you replace the actual OB values with the student T values.
The simulation, a lot of the values that you get are also correlate. So that's where the student teams do it. So they're taking into account.
Yeah. So again, excellent question. The question is, in a large situation, particularly in simulation settings, the Y's are going to be correlated, heavily correlated. Think again, the first example. The Y1 is the waiting time of the first car, Y2 is waiting time of the second car. If the first car has waited a long time, highly likely the second car would have waited a very long time as well. When William Gossett considered this situation, he assumed that the data were independent. Highly unlikely that in our settings, in simulation settings, the data would be independent. This method explicitly accounts for the dependence. That is why if you did what Gossett did in a dependent situation, you will be misled into thinking that the confidence intervals are shorter, because the intervals that you construct will be shorter, but incorrectly so. Okay, so the batching distributions explicitly account for the dependence. So yes. So,
An idiot question, but in the last slide you showed where you have your confidence regions, is there a sort of a reason from physics or mechanics why they're not static?
Yeah. In the particular example that I took, it turns out that the variability is actually proportional to the deflection. So as you go further and further out, so this cantilever beam is attached to the wall here. It deflects far less on the left than it does on the right. And it turns out that if you take different beams, the variance in the deflection is actually proportional to the expected deflection itself. And that's the reason why the confidence region is itself wider in locations where the deflection is high.
And they're not symmetrical about the expected value that's in the middle.
Right. It is not symmetric because here, for example, let's say for the moment that this is the expectation, because in this location at this X, the deflection is higher. The variance itself turns out to be higher, and the corresponding region confidence interval will turn out to be wider. And so you're asking about the symmetry here. I see what you mean. In a nutshell, again, it's symmetric because it cannot go further. The beam cannot deflect to the top, meaning that there's a lower bound 0. And because of the lower bound being 0, the deflection on the bottom side is lower than the deflection on the deflection on the upper side is lower than the deflection on the downside because of the 0 being a bound. Yeah. Celine? Yeah.
The amount of overlap is an important parameter that we would probably want to choose. So would you imagine some sort of cross validation? Is there a way of understanding like the amount of overlap is what?
So because you asked that question, I'm actually going to go right to it. The question that was asked is, it seems like the number of batches and batch size, essentially a restatement of what you just asked. The batch size and the number of batches to a large extent determines how much overlap there is. And this is really, really important. And it turns out that it is an open question at the moment. But broadly, we have very clear insight on how it affects things. So let me explain a little bit here because I believe I do have a couple of minutes. So one of the ways by which you assess confidence regions or confidence intervals is using two metrics. The first one is called coverage error. Coverage error means that suppose I say that I want a 95% confidence interval. Well, does the interval that you're reporting actually cover it with 0.95 probability or not, right? So that is what is called the coverage error. Now, a trivial way by which I can cover, or I can give you an interval that covers the true quantity 95% of the time, is negative infinity to infinity. That's a silly interval that I can give you. It'll always cover it. So in order to account for that, we also report something called expected volume or expected width. We want intervals that are short that also cover 0.95 with 0.95 probability. So these two are key metrics, quote unquote. It turns out that using big batches ensures that your coverage error is small, right? So that's really, really important. But using big batches also ensures that your expected width turns out to be high. Number of batches is also very important. It ensures that the expected width is small. So these two are playing a role, but we are at the moment trying to really carefully clarify how these are going to be. In all of our experiments, repeatedly, somehow there seems to be this magic region of about the batch size should be about 15 to 20% of the total data set size. So if n is the total data set size, the batch size should be about 0.2 times n, it turns out. And that there appears to be an optimal sweet spot with respect to the number of batches or batch size. This appears to be a really deep question that we are still working on at the moment. Christine.
So with the batches, you could see that you could do one long simulation run and take your batches and then use that to get your answer. Do you still recommend running the simulation more than once?
So interesting question. So I very carefully avoided the question of a single long run versus multiple runs, because I happen to think this is a question that is separate from constructing confidence intervals. So Y1, Y2, Y3, and so on, Yn are post having decided whether you made a single long run or individual runs. I happen to think that. My prescription is to treat this as a separate question, because the considerations that can go into deciding whether you should use a single long run or separate runs are different, is what I think. But irrespective of whether you do a single long run or multiple runs, the same methods apply. I don't know if that makes sense.
I can see an argument why you would do more than one run, because the starting position in certain simulations, the starting position will mean you may go on a completely different trajectory. So I guess there's a danger of bias.
Yes, yes, true. That's correct. So one thing that I've skipped over is that there is the question of a warm-up problem in simulation. If you do a single long run, I have assumed whenever I've stated Y1, Y2, Y3, and so on until Yn, that these are all coming from the steady state distribution. So in practice, when you're actually running the simulation, you have to take care of what is called the warm-up problem. I've completely shoved it under the rug. So now you have to actually talk about, that again is a separate question. Maybe you have to throw away some amount of data before you actually collect it. Yes.
This one question I was kind of talking about the nature of your confidence region. Maybe can I perhaps have a look at the real things? Yes. Now, when you calculate confidence limits, are you referring now to the level of confidence applied to one point or to the entire curve line?
Indeed, it is the latter. Yes.
If you actually calculate the difference of points, is such the individual confidence limits pretty sure. So that several
very much.
Three simultaneously.
Very much so. So it is indeed the latter, where we are considering all points simultaneously. So this object, that is why this object that we're thinking about, the data that I was talking about, is an entire function and not point-wise. It's considered function-wise or path-wise. Russell?
Yeah, so I want to go back to one of your giants on whose shoulders you're standing, Jim Wilson.
Yes.
So when you talk about your T for overlapping batch, is that making an assumption of normality for the batch?
So not directly. Well, the assumption that we are making is the following. So maybe I can go back here, choose an appropriate slide. Let me actually give you the precise assumption that we are making on theta hat n. So Gossett, by the way, made the assumption that the individual y's are IID normal. In this case, we are not making an assumption on any assumption on the individual y's, but I'm making an assumption on theta hat n as n tends to infinity. In particular, I'm assuming that theta hat n obeys a central limit theorem as n becomes larger. That is a precise assumption. Yes.
So then I think based on what you said for R2, you're going to cover this later, but then you're competing with bootstrap methods that don't require an assumption.
Yes, indeed. So, so maybe I can go to that R2 right there. So if you don't mind, Russell, I'm just going to give a 20-second summary of this particular point, R2. Now, it turns out that over the last 30 or 40 years, as batching was happening, for example, in a small portion of the simulation community, simultaneously, bootstrapping was being developed, starting in the late 1970s by a person named Brad Efron at Stanford, and several others who participated later. They developed a method called bootstrapping that has gone on to be pronounced as one of the greatest discoveries in statistics, all of statistics. And it has become really an omnibus way of doing uncertainty quantification or confidence interval construction. Now, batching, as I've stated it now, as Russell correctly pointed out, competes with bootstrapping, and bootstrapping assumes less than what we assume. Absolutely. Two things there. We have noticed that in a lot of settings, theta hat n satisfying a CLT is valid. In a lot of settings, this happens. In settings where it doesn't happen, bootstrap is the only game in town, right? In settings where theta hat n does satisfy a CLT, it turns out that because bootstrapping is not using that information, whereas we use it, our confidence intervals are narrow. Right? So that information is being used. I think I've run out of time, right, Christine?
I think probably about 10:30.
Oh, fantastic.
Maybe summarize and then final question.
Sure. So maybe I can also take 30 seconds to state R1 and R2 for the practitioner. By the way, this division between practitioner and theorist has always troubled me. I feel that it's a very artificial difference. We should be thinking in terms of practitioner informing the theorist and the theorist informing the practitioner. This is not a clear line at all in my mind. But having said that, hopefully I've at least kind of inspired you or sparked you into thinking about a few things. In particular, consider reporting an uncertainty metric alongside the simulation estimator. So to repeat, we as simulationists are exceptionally good at reporting theta hat n, but we are not so very good at reporting uncertainty metrics surrounding theta hat n. And this, hopefully, I've convinced you that this is crucial because this corresponds to decision making. If you're really, really confident about your estimate, you can make confident decisions. If you're less confident about your estimate as reflected in your uncertainty metrics, maybe you have to hedge against it. So reporting this uncertainty metric, I feel, is very, very important. And I feel this is particularly easy now with a method such as batching or bootstrapping and subsampling, number one. Second, so much so that these uncertainty metrics, I feel, should be incorporated into simulation software because the method is fairly easy. We have tables as well that which are available in the form of code. So that is the second urging point as far as this talk is concerned. So let me stop there and take any questions, any further questions you might have. Thank you again for this opportunity.
Any further questions? So when you are considering using this battery, would you say that you typically need to have more samples in your data to start with, so that those batches are most likely really small, versus say running multiple simulations, you can run 100 different sequences, in that sense, would you say that you can consciously choose the button along that how?
The way the procedure is constructed is as an external model. So in other words, you don't have to do anything special in order to report an uncertainty metric. So whatever runs you've already done in constructing a data have N, you apply this method on top of it. You don't do anything extra. Now, if the uncertainty quantification metric turns out to be unusually big, as a result of having constructed your algorithm or when you report it, it's at that time that you decide, I'm too uncertain about whatever I'm reporting, maybe I have to resolve. And so this is external to modeling between. Yes.
You've shown us an example where a sample can be included in 2 batches, and you actually increase that number in a single sample be part of 3 or more batches, and are very dangerous to them.
I'm not sure I'm following your question. So
when you overlap the batches, some samples are part of 2 batches, and there be even more than that.
Oh yes, very much. In fact, so let me go back here. So in this picture, let's take the extreme case. The second batch can begin at the second observation. In fact, I recommend it. That's called fully overlapping batches, where you overlap these batches as much as possible because you're squeezing out as much information as is available. There is a downside to it. The downside is that you have many, many batches, and if computing the estimator from each batch is going to take very long, as will happen in an optimization context, you'll pay the price in terms of computation. But if computation is not a bottleneck, I will recommend that you overlap these batches as much as possible. So in that case, B will be 1.
You mentioned about the they're not necessarily integrated. Would the goal stand to be to take this assessment with that CDD compensation results or that's actually break down the same.
Yeah, that's an excellent question. So in the context where you have a time series, by time series, what I mean is the Y1, Y2, Y3, the fact that Y2 comes next to Y1 and Y3 comes next to Y2, the order is very important. If you actually jumble up the order, as bootstrapping does typically, then you're going to destroy it. In fact, it's not a very wise thing to do, is what I would say. However, your idea is still very, very good, because I think you could extend this method to a situation where you don't consider just batches of size M, but you consider batches of size M, batches of size M-1, batches of size M-2, and so on. And you can create far more number of batches, quote unquote, while maintaining the integrity of order. I would think that that estimator would probably be better than what I've shown here. So there you're taking all possible contiguous batches of all different sizes. So there will be a second order effect that comes in that will make my confidence interval even better.
So with one of the examples you spoke about, simulation optimization, you can understand that maybe if you look at the uncertainty of your optimal solution and quite large, that you might want to go back and think about how you're optimizing the problem first. Let's say, do you envisage that this could be used in some sort of simulation optimization methodology?
Yes. In fact, one of the algorithms that we've been working on recently does precisely that, where we are using a method of decide to progressively decide how much to sample as we solve the simulation. So early on, for example, as we're getting closer and closer to the optimal solution, if our confidence intervals remain really large, then you collect more observations and solve your optimization problem. So that's, I'm not giving you all details, which takes apart, but the point is there's a trade-off between how far away you are from the optimal solution and how much you sample. These are linked. And the characterization of that linkage comes from confidence. So exactly.
Just following from that question, you recommend for practitioners quoting an uncertainty metric. How do you think that practitioners should use that metric, or what would it help them to do? Are you just proposing they quote it, and then just that would be a metric on how uncertain things are, and how different is that from what does it give you more than say a confidence interview? How do you expect practitioners to use it?
That's a good question. So I would think, for example, at the minimum, it would prevent practitioners from placing too much importance on a single number. So imagine an alternative situation where you're not reporting an uncertainty metric. Let's say you're reporting just theta hat n, and you're making a decision based on it. While in reality, the uncertainty associated with theta hat n is very, very large. You simply do not report it. You end up making a decision based on that one number, quote unquote. While in reality, you would have hedged. In a situation where that uncertainty is very, very large, you may have said, yes, this theta hat n is asking me to make a particular decision, but really I don't believe it too much, because my uncertainty is too very large. So I'm going to make a decision. So a really nice example is what is called the Markowitz portfolio optimization problem in finance, where you're actually trading off mean and the variance in a portfolio. So in a situation where you're making decisions to maximize profit in a financial portfolio, in a situation where you consider only the mean, for example, you might make a particular decision. But the point of the Markowitz portfolio, for which he won the Nobel Prize, by the way, it was that he said he urged us to think about both the mean and the variance. So this is essentially a take on that as well. The point is confidence intervals, variances, for example. Our confidence intervals is basically a way to quantify the variance associated with whatever you're reporting as well.
So what does this give you more than the say of variance? And do you have any scale on what's an uncertainty metric? What scale is uncertain? Is it a percentage? Is it, if it's 50%, then it's seriously got a problem, or if it's 5%, it's fine? Or can you put a scale on things, or is it just a number?
So I would say that depends a lot on the particular application that you're considering, right? So what you would do, for example, in a situation where you have to deal with the risk associated, let's say, with the probability of, let's say you're doing surveillance in an airport, and you're estimating probabilities associated with a bad event happening, and you report a standard error there. That is very different from, for example, the standard errors associated with travel times on a highway. These two are very, very different contexts. So I suspect that there isn't a single answer. The best thing to do would be, I would think, would be to report a theta hat n and a standard error associated with it, or a confidence region associated with it, and ask the person who's the specialist in the domain to make a decision based on it. I would be very nervous to give a single universal standard as far as making decisions are concerned. Russell?
Josh, I like your thoughts about presenting the decision maker with a histogram instead of a confidence interval. Because you have that key overlapping batch distribution, you can construct an artificial histogram at the end to them that has no particular confidence limit on it and let them interpret that. What do you think about that approach to support decision support?
I actually completely agree with that. In fact, I'm very nervous of reporting confidence regions simply because they are subject to massive amount of, they're vulnerable to misinterpretation. So for example, let me explain a little further. Whenever I say probability of data living in C sub n is equal to 1 minus alpha, usually people interpret that in a Bayesian software, where you say, think of data itself as a random variable and giving you a set, and then I'm saying the probability of data living in that set is 1 minus alpha. While in reality, the interpretation is quite different. That probability is across practitioners. If a large number of practitioners perform the same experiment, 1 minus alpha fraction of those practitioners will report CNs that contain protein. It's sort of a nuanced interpretation, very vulnerable to misinterpretation. So I've been trained by an advisor, PhD advisor, to not think about, to be very careful about confidence regions. And so I'm a little skeptical there. Reporting histograms is an excellent idea, but I also worry about where there again is, I worry that the practitioner might be a little more, maybe a little too nuanced for a practitioner, I do not know. But maybe it's just a matter of being used to it. So report the histogram again and again and again, and ask the practitioner to live it.
Could we give our thanks to Raghu for next week?